In this video, we want to find out how the Lagrangian of a theory must look like in order to describe the electromagnetic field, which is the foundation of Maxwell's equations. We will use the following notation. A mu is the electromagnetic fore potential. Using A mu, we can construct a gauge-invariant tensor, F mu nu, which is a theoretical tool that enables us to calculate the electric and magnetic fields that we can actually measure in an experiment. Also, a gauge transformation for the electromagnetic potential means adding the derivative of some function f to the electromagnetic potential. Let's move on. Since we want to construct a theory based on what we see and measure experimentally, we can impose some constraints. First, we want to use a field theory in 4 space-time dimensions. Field theory is the modern view of physics, and it works really well. Second, the only field we want to consider is the electromagnetic field A mu, sometimes called the Maxwell field. We do not consider any electrons or quarks, just the electric and magnetic fields. Third, we impose Lorentz invariants. Since we want our theory to be valid in any reference frame, we better make everything Lorentz invariant. 4. We also impose gauge invariants. We know that we have gauge invariants in electrodynamics, so let us also include it here. And 5. In the construction of the Lagrangian, we use at most 2 derivatives in any term. This might not be obvious at first, but terms with more derivatives attached to them lead to so-called irrelevant terms. Now we can work out how the Lagrangian must look like. The first condition means that we should work with a Lagrangian density instead of a Lagrangian function. For the second point, we write the action as a functional of A mu and the Lagrangian as a function of A mu in all possible ways. In order to be Lorentz invariant, we always have to pair up our indices. This drastically reduces the possible terms inside the Lagrangian. Number 4 implies that our building block for the Lagrangian should be the electromagnetic field strength tensor, F mu nu, instead of A mu. This is because F is the smallest possible combination of A mu that is also gauge invariant. Finally, for point number 5, only 2 terms remain in the Lagrangian. We cannot use more than 2 f's in one term, since they each contain one derivative, and we cannot attach a derivative to a single f, because then we would have one unpaired index. This leaves us with 2 copies of the field strength tensor and 2 possible ways to contract the indices. We are free to use the epsilon tensor, since it's basically just a number, plus minus 1 or 0, depending on the indices. We are almost finished. There are 2 remaining remarks. First, we can ignore the second term for now, since it's a so-called boundary term, which does not contribute to the equations of motion. Second, it is convention to choose the constant c1 to be equal to minus 1 over 16 pi. So finally we have our result. This is the Lagrangian density for the Maxwell field in a vacuum. And that's pretty much it for this time. Thanks for watching.